Hello, sir.
Hello.
Hello. Am I audible to you, sir?
Hello.
Hello.
Voice.
Okay.
Not getting voice.
Shashi, sir, am I audible to you?
Yes, ma'am. Hello, sir. Good afternoon. Can you hear me?
Hello.
Sir, I think
Hello.
there is some fault. Your mic is working.
Hello. 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 Is my voice audible?
Yes, sir.
Yes.
Voice
yes,
is
sir.
audible? Okay,
Yes.
okay. So shall I start now?
Yes, sir.
Dr. Neelam, shall I start now?
Yes, sir.
Okay.
Yes.
So good afternoon, everyone. So today I am going to speak on characterization of natural geotextiles. What do you see in this? I want to have some interactive kind of session. Anyone can interact with me. What do you see in this picture? Hello? What
Yes,
do
sir.
you
You
see
are
in this
audible.
picture? This is nothing but showing you the coconut plants, and in the second slide I am showing you the two pictures. One is showing you the brown coconut, other one is the green coconut. Now if you see the brown coconut, you have the shell. This is the shell. This is the pith in which the fibers are embedded. Whereas in green coconut, if you remove the upper part, you will find similar kind of things. The fibers and the pith both are going to be present there. Now, the question is, whenever we remove the pith along with fibers from the shell of the coconut, now how to extract the fibers from this? So for that, we need to go for the retting operation, and this retting operation is nothing but we dip the coir pith along with fibers in water, and the duration actually varies from 6 to 9 months depending upon the type of fiber. Basically, if because there are two types of fibers in color, which we'll talk about later, but right now I'm just showing you that the pith is dipped into the water for 6 to 9 months, and this entire process is known as the retting operation. Now after the dipping the coconut pith in the water, now what we do is we take it out, dry outside, and after drying we beat them with wooden mallets, and then we separate the pith from the fibers. So this entire process is called the retting operation. Now after the retting operation, we get two types of coir. One is shown in the first picture, which we call as the brown coir. Other one is known as the white coir. And third picture basically tells you about the separated fiber separated from the pith. So this is a heap of pith which is there. So once the fibers are separated from the pith, the next step is to make a yarn from the fibers. So the next slide basically tells you that how we prepare the yarn from the fibers. So these two pictures show you the yarn which we have prepared from the fibers. Now the question is, what is coir? So the processed fibers which we obtain from the husk of ripe coconut is known as the coir. That means whatsoever the after doing the processing, whatsoever the fiber we obtain, whether they are brown in color or white in color, we call them coir fibers. Now if we look at the traditional uses of the coir fiber, long back jute was used for the erosion control applications. And if we look at some positive attributes of these naturally available fibers, they have got very high water absorption, they have the drapeability ability, and they have the ability to make a small check dams when we put them on the slopes. A woven kind of material is going to have this. So formation of the mini check dams will reduce the or the retard the velocity of the water flowing down the slope. And there's a term I am using here, drapeability. Drapeability means a material which can take the shape of the ground profile. That means if the ground is uneven, the material has that ability to take the shape of the ground profile. That is the drapeability ability of the material basically which we make from the coir fibers or the jute fibers. Now if we look at the uses of this coir fiber, long back in 1983, the first trial was made by one of the researcher. In India, mesh matting, we started using mesh matting since 1988. At present, no systematic use in India actually is available. Those few trials are being made in the southern part of our country, where we are using them for the roads, especially the unpaved roads over the soft soils. Now coir as an engineering material. So if you look at the coir fibers, their length is varying between 50 to 300 mm, diameter between 100 to 400 micron. Longer fibers, they are thicker or heavier than 15 Den PP fibers. 15 Den basically is a textile unit. Their tenacity is around 15 centinewton per text. Text is a unit of length, and centinewton is basically similar to kilonewton. So you can convert this centinewton to per unit text. So these are and the elongation at break is around 40%. So you can imagine that how long this fiber can take while during failure. It can extend up to 40% of its original length. Now in the conventional spinning process, all coir fibers, they are bunched together and twisted to a two-ply yarn. That means we make two yarns, and those yarns are twisted together to create a single yarn. Later on, this single yarn is used for making the woven mesh mattings, and many varieties of non-woven geotextiles are also available. So these non-woven geotextiles, they are air-laid, needle punched, adhesive bonded, stitch bonded. So variety of technique basically we use to join these loose fibers together. Needle punching is one of the operation. Adhesive is another operation. Stitching is a third operation. So any of the operation can be used in order to create the non-woven types of geotextiles. Now if we look at the area and production of coconuts in India, I have taken the data is available up to 2018-19. So here you see Andhra Pradesh was producing around 1,567 million nuts. And the highest I think is the Kerala, which is producing 7,683.55 million nuts. So this is the production. That means if you see all this table, you will find that the south part of our country, they are the maximum producer of the nuts. And these nuts, they are used to extract the fibers, and fibers are used to make the yarns, and yarns are further used to to make the geotextiles. So this is the order of sequence how the things are going to be there. Now if we look at the types of the fiber, the very first type of fiber we have the brown fibers. So brown fibers basically they are derived from a matured coconut. The coconut which is brown in color, the fibers what we extract from the pith of the coconut, those fibers they are brown in color, and we call them brown fibers. And these brown fibers they contain more quantity of the lignin and less quantity of the cellulose. We'll talk about these two terms, lignin and cellulose, later. The other variety of the fiber which is available is the white coir. So white coir is derived from the green coconut. That means the green coconut gives you the white color coir, and they are weaker, they are smoother and finer and weaker. But that's why they are spun into yarns, and yarns are used to make mats and ropes. And that is why we don't use them for making the coir geotextiles. Now if we look at the composition of the coir fibers, so in this slide, you see the composition of coir fiber. Lignin is around 45%, cellulose is around 43%, and rest of the components they are there, which comes out to be around 12% or so. So because of this lignin, higher percentage of lignin in the coir, they show better durability in comparison to other fibers such as jute fibers, hemp fibers, and there are other so many natural fibers they are there. So in comparison to other fibers, because of higher percentage of lignin present in the coir, they show better durability when used in conjunction with soil. Now this slide I am showing you some of the physical and mechanical and chemical properties of the coir fiber. So if you look at the specific gravity part, it is having 1.15, which is very light in comparison to the soil. So slightly more than water, but it is less than majority of the soils. Fiber diameter 0.1 to 0.8 mm. Length of individual fiber 250 mm or more. Color depends upon the treatment process. How you do the retting operation, that basically, and what is the source of the fiber, that basically gives the color. If it is derived from the matured coconut, it is going to be brown in color, and if it is derived from the green coconut, then white is going to be the color. So if you look at the young modulus is going to be around 4.5 giganewton per meter square. Rigidity modulus 0.18 Newton per mm square. So I am just giving you this data just to tell you that these materials they have adequate value of the modulus and the strength. If you look at the tensile strength, it is 160 meganewton, right? Electrical resistivity, thermal properties, specific heat, thermal conductivity, other calorific value, they are highly inflammable. So that means though this particular slide or the properties mentioned on this slide may not be much useful to the civil engineer as far as their application aspect is concerned. So sound absorption properties, it is there. Water absorption properties, it is there. It is good for erosion control application. Water absorption property of the coir is good for erosion control applications, because when we lay them on the slope, they absorb the moisture from the soil, and you can put certain seeds to grow the grass or to grow the plantation over the slope. So that way they will help us in controlling the erosion. Now we'll move to the different classifications. Now if you look at the classifications, the first category we have the erosion control nettings. So these nettings can be made of the natural material or they can be made from the polymeric material. So they are basically biaxial nettings where the yarns are run at right angle to each other in two different directions. And whatsoever the net we obtain, we call it erosion control nettings. They can be of polymeric material or they can be made from the natural material also. The other category is the erosion control meshes. So the other category is the erosion control meshes. They are the open weave geotextile meshes formed into 2D matrix. So again, if you compare them, they have higher tensile strength in comparison to the third one, which I am going to show you right now. The third category in this is the erosion control blankets. So erosion control blankets, they are used for controlling the erosions. They are loose web fibers which may be joined together either by the needle punching operation or by stitching with the polypropylene yarn or jute yarn or some PP yarn. So any of the yarn can be used in stitching in both the direction or in the single direction depending upon the requirement. So erosion control blankets, they are exclusively used for the erosion control applications. Now coming to the photographs. So I am in this picture, I am showing you few nettings or meshes. They all are made from the natural material, that is the quern yarn. So if you look at the very first picture, it is showing you H2M3 and H2M5, H2M8, H2M6. So what difference do you see in all these four pictures? You see the aperture size is varying. So larger is going to be the aperture size, smaller is going to be the tensile strength of the material. So if you see H2M6 is going to have the lesser strength in comparison to H2M8, and H2M8 is going to have larger strength than the H2M5, and this is going to have the least strength, and H2M next higher, and this H2M3 is going to have the maximum strength among all the four nettings or the meshes which we are having at present. This is all because the aperture size of H2M3 is much smaller in comparison to rest of the types of the meshes or the nettings. And indirectly, if we want to see the reason for this, it is directly related to the number of yarns present per meter length. So if you see the H2M3, number of yarns are going to be more per meter length in comparison to rest of the types of meshes or the nettings. So more number of yarns, more strength. Less number of yarns per meter length, lesser is going to be the strength of that particular material. Next slide, I am going to show you the rolled erosion control blankets. So these are the blankets which are available in the roll form. The roll length and width varies from manufacturer to manufacturer, but normally between 5 to 5.5 meter width and 50 to 200 meter length, they are available in the market. So depending upon the requirement of a particular site, we can choose the appropriate roll. Now if you look at the erosion control blankets picture, the more details I will show you in the next slide probably. This is the much closer view of the erosion control blanket. So here you see these are the loose fibers. All these loose fibers, they are stitched in one particular direction by the use of a PP yarn. This is a polypropylene yarn which is used in stitching in one direction. This is one way of creating some tensile strength in these non-woven kind of products. Otherwise, it is going to be a loose web, and loose web doesn't have any tensile strength. That's why in order to have a little bit strength, tensile strength, we need to stitch them along one direction or the other direction by the use of either the PP yarn or the jute yarn, or we can use some other kind of yarns in order to develop a little bit tensile strength in these kind of materials. Otherwise, when we use them on the slope, a little bit tensile strength is required. Otherwise, they will break automatically because they don't have anything to keep them together. So that's why the stitching is required along one particular direction. And this stitching is nothing but we call them scrims. So this technical name for these stitching, we call them scrims. The scrims can be made of the polymeric material or the polymeric yarn, or they can be made from the natural fibers also. So this is another picture of the erosion control blanket where the netting is stitched together by the use of some jute yarn. So white color yarn is a jute yarn. This is a single yarn which is used for stitching the loose square web in one particular direction. So this is another picture which is showing you the stitching is done with the 2-ply yarn. Now 2 yarns are used together for doing the stitching. If you make the comparison of this one with the previous slide, you will see that this product is going to give you larger strength in comparison to the previous one, because here we are using 2 yarns together to stitch the loose square web in one particular direction. So this is another picture of the erosion control blanket. So it is provided with jute scrim on this can be provided on a single side or it can be provided on both sides. So because of the presence of this scrim, this is giving you some strength in one particular or the other direction. Because loose square web doesn't have the strength, non-woven material loose web doesn't have the strength. The entire strength is governed by the scrim or the yarn which we use for the stitching purpose. So this picture just I have included just to show you that when we use them on slopes for the erosion control application, so we are to simply unroll the roll in the downward direction. So things will go automatically. Then you have to bury them into ditches at the bottom as well as at the top. And the central portion we just drive them by the use of the wooden pads at different spacing. Along the slope, we provide these wooden pads at different spacing. And the roll of this so that the entire thing may not slide down. Now coming to the durability aspect of the coir geotextiles. So if you look at because the durability aspect I thought better to be discussed here. Reason being, when we are recommending them for the application to the civil engineering related projects, there this issue is the main issue, that whether these materials are durable or not. So the very first study, it was started long back in 1991 by one of the researcher. So this researcher gave one conclusion that whether the coir rope basically he used in his study, and the coir rope was put inside the fertile soil. And after 1 year of the incubator test, the entire thing was put in the incubator at a fixed temperature and humidity. Then after 1 year, he tested the strength and he found that the coir geotextile was able to retain 20% of their original strength. That was the initial study which was reported long back in the year 1991. Later, the same author, he tried the same basically coir fibers or coir yarns in water, and he kept that material in water in the shower room, and that material was kept in the shower room for 160 days with the condition to simulate the traction effect while flooding. And after 167 days, he has found that coir had almost no damage. There was no damage to the coir after 160 days of putting them in the shower room. So this was the initial study which was conducted long back in the year 1991. Then in 1992, there's another author. He reported the loss in strength of coir rope after 10 months in pulverized ash was around 20%. So again, after 10 months, he buried the entire thing in the pulverized ash and under the controlled humidity and temperature condition. And after 10 months, he found that there was no damage to the coir. So this is another study which was reported in literature. Then in the year 1995, if you look at this work, I am actually presenting from the PhD thesis of Dr. K. Bala, who did his PhD in 1995 from IIT Delhi. So he basically what he did, he picked up a variety of coir geotextiles and put them under different environment, right from water to soft clay, high organic content soil, or burial in sand, and even the manure is also used in this particular study. Though I have not included that data, but I'm just telling you that lot many different kind of media was tried. So on the basis of this entire study reported in this particular PhD thesis of Dr. Balan, they came to one conclusion that the overall life of the coir, it varies between 2 to 3 years, and the brown coir degrades at about 20% in 7 months at a faster rate in comparison to the white coir, which is about 10% in 7 months. So meaning thereby that the degradation is going to be there up to the order of 20% in case of brown fibers, brown coir, whereas it is going to be around 10% in a period of 7 months in case of white coir, right? So we need to consider all these aspects in mind while recommending their application to the civil engineering related problems. Now I'm coming back to the exact topic of today's topic. This was all the background I wanted to have because people may not be aware about the material. So I thought it to tell you some basic things about the material about which I am going to talk about right now. Now coming to the characterization part, basically in characterization, what we do is we study each and every component of the naturally made geotextiles, whether they are the woven geotextiles or the non-woven geotextiles. Here we basically study that what are the things which are contributing to the strength in these materials. So this kind of, we separate each and everything together and then we categorize that why we are getting more strength in one direction in comparison to the other direction. So this entire process actually is known as the characterization of the material as far as the civil engineering aspect is concerned. So we conduct other types of tests also, the SCM, the FTIR, and the FEM, the SCM and your SCM and XRD in order to go for the further chemical characterization of the things. But right now, from the strength point of view, we just want to see that what are the things which are basically responsible for developing the strength in these kind of materials. Now the characterization work, it was started long back in the year 1982 and 1984 by these two researchers, and they picked up the polymeric geotextile, woven geotextiles, and they studied the behavior of polymeric woven geotextiles, and finally they found that these woven geotextiles were most influenced by the aspect ratio greater than 4. That means if the aspect ratio is greater than 4, their strength actually is going to be affected, and the specimen gauge length is less than 50 mm. And the non-wovens were influenced by the aspect ratio less than 2 and specimen width less than 100 mm. This was the initial studies which were carried out by these two researchers using a polymeric type of material. At present, even today, we don't have the well-defined procedure for testing the coir-related materials. We'll talk about those issues later. But this was the first study which was reported long back in the year 82 and 84. Then, in the year 1986, again, the work of these previous two researchers, this was extended, and what they did, they took a 200-meter wide specimen and they conducted the test using a 200 wide test of the natural polymeric material, and they found that the woven that the strength of this 20 centimeter wide specimen of the polymeric material is basically, it is giving you 10% overestimation of the tensile strength, and in case of non-woven, it is underestimating the strength, say about 20%. So this was the another you can say study related to the characterization was there, which was reported long back in the year 1986. Then after 86, another study was reported by Karunarathne in 1992. Now in this study, if you look back, he has basically done the compressibility and the thickness related studies of these the polymeric related materials, and some natural materials were also used in this study. So what he concluded from this study, that the jute matting under different pressure shows around 90% of the compressibility, and this 90% of the compressibility is reached in a 5 minutes upon the application of the normal load. So this was the main conclusion which was drawn out of by one of the study reported by Karunaratne in 1992. Now, based on this study, it was recommended that the jute geotextile, the thickness can be measured 2 minutes after the application of the pressure. So that means if you want to measure the thickness of natural geotextiles, so in case of jute, this study was reported. So you can measure its thickness after the application of some normal pressure, and that is for a period of 2 minutes. So this is required because now the question is why we apply a pressure to measure the thickness. Reason being that these material we are going to bury them inside the soil at certain depth below the ground level, or even on the slopes also, or in that some depth below the ground level. So the height of the depth multiplied by the unit weight, it gives you overburden. So that means these materials are going to be subjected to that much overburden. Therefore, their exact thickness under that overburden is required. So that is why we measure the thickness of these materials corresponding to that particular overburden pressure. Then Karunaratne in 1992 further reported that the strength has no relation with aspect ratio, length and width or strain rate up to 20% per minute for the jute geotextile. So this was the another study which was reported by Karunaratne in the same paper. So from this, now keeping all these previous studies in mind, then Professor G.V. Rao, K. Balan and myself, we three people, they were involved in this study, and what we did in this study basically, we picked up all the ASTM standards which were developed for testing the polymeric geosynthetic, and all those test procedures and the strain rates, they were applied to the naturally available coir fibers and coir geotextiles. So based on this study, I am showing you, if you are able to see this diagram, on the y-axis, the thickness is there. On the x-axis, we have shown the time in minutes. So here I am showing type A, type B, type C, type D, type E. So these are all combination of the woven and the non-woven types of geotextiles. Now, all the thickness of all these materials, they were measured under a pressure of 2 kPa and after 1 minute application of load. So, though the time was varied and the plots were made, so if you see about at a time of about 1 minute, at this 1 minute time, beyond this, there is not much change in the thickness of this material. So, the first conclusion which was drawn out of this study was that if you want to check the thickness of the coir geotextiles using the test procedure which were laid for the polymeric geosynthetic product by the ASTM, you can measure their thickness upon application of 2 kPa load and up to a period of 1 minute, and after 1 minute you can take the actual reading for the thickness of that particular material. The another conclusion, if you see the same picture, maybe in some other slide I will show you that, regarding the compressibility issue. So compressibility issue, the compressibility of the non-woven geotextile as well as the woven geotextile, they were studied under different normal load. So the normal load was varied between 1 kPa to 10 kPa. And on the x-axis we are showing you the time in minutes, and the thickness is shown on the y-axis, and different curves they are for the different types of products. So you will see that the larger compression is observed in the non-woven types of geotextile in comparison to the woven geotextile. That means the woven types of geotextiles, they undergo more compression in comparison to the woven types of geotextile, because this aspect is required to be studied when we use them for bearing capacity applications or for improving the bearing capacity over soft soils and all that. So there this because under load some initial compression is going to be there, because these materials are going to compress under the load. So that compressibility has to be subtracted from the total settlement basically, which we obtain below the structure or below the footing, right? So this is that's why the compressibility study is required and is important from that angle. Now coming to the another aspect, if we look at the ASTM standards which were developed for testing the wide width tensile strength of the materials, and the wide width tensile strength of the materials, for that the different ASTM procedures are available. So the same procedures were followed in case of testing the tensile strength of the coir geotextiles. So here you see that the rate of strain which was varied from 10 to 300 mm per minute, and then the tensile strength of the material was measured and the rate of strain is shown on the x-axis. So here you see that if you see this average curve where my cursor is there at present, from this point onward to this one, there is not much change in the strength. Though one of the point is at lower value, but other points are at almost similar range. So this indicates that the strength of these materials can be measured by using a strain rate of 10 mm per minute, and this 10 mm per minute is basically the recommended value for the testing of the polymeric geosynthetics, which is given in the ASTM standard. So that means for the naturally available coir geotextiles, especially the woven kind of geotextiles, the same strain rate we can basically use for testing the tensile strength of these materials. Then the same basically study I have shown in terms of the tensile stress versus strain curves. So again you see here the strain rate used is 2 mm per minute, 10 mm per minute, 100 mm, 300 mm, 500 mm. So all these curves, they are very close to each other, very close to each other. So that means if you test these materials for the tensile strength, if using a strain rate of 10 mm per minute, so this is going to give you a fairly accurate value of the tensile strength. And the another study which was conducted during reporting of this data in the paper, that was what should be the size of the sample of the coir geotextile. So here a lot many sizes of the coir geotextile they were tried, and the one size was 20 centimeter by 10 centimeter. This was also tried. So the main conclusion of this study, that the value what we obtain corresponding to 20 centimeter and 10 centimeter length specimen, the tensile strengths are very close to the actual one. So therefore the main conclusion drawn from this study was that for testing the tensile strength of the natural coir geotextile, we need to have the sample size of 20 by 10 plus 8 centimeter on either side you can have for the gripping of the specimen, and the strain rate which is to be used, it is to be 10 mm per minute, right? So this was the conclusion which was drawn from this particular study. So these are the tensile stress versus strain curves. So here you see that if you test the material along the width and along the length of the roll, you will find lot many variation, and this entire variation in the strength is because of the different diameter of the yarns which are used for making the woven types of geotextiles. So here the yarn diameter is different, and therefore the strength in different direction. That therefore if you test 5 specimen in the roll, the main direction of the roll, which we call as the machine direction, and 5 across the width, which we call as the cross machine direction. So you will find a lot many variation in the tensile strength. So here you see that all 1, 2, 3, 4, 5, 6, there are 7 different curves they were tested. So every curve actually showing you a different value of the tensile strength, because this difference you are getting because the yarn used at different location for the woven geotextile may not having similar diameter. So that's why you are getting different tensile strength values. So even the strain at failure, you are getting little bit variation. Now the question is which value of the tensile strength and the strain is to be picked up or is to be reported. So for this we need to perform the statistical analysis. Now in this table, I am showing you four different types of geotextile: type F, type G, type H, type I. If you see the number of yarns in the bark direction or the machine direction, they are 30 for the first one, 40 for the second, 100 for the third, and 250 for the fourth one. Number of yarns in the left direction, that is the cross machine direction, 22, 40, 67, and 143. And mass per unit area, 335, 360, 610, and 1335. So here you see, larger the mass per unit area, larger is going to be the strength. So mass per unit area is also related to the giving you the indication that the material is going to have the larger strength. Smaller is the mass per unit area, smaller is the tensile strength. Again 360, the tensile strength we obtain is 6.34. If you have a 335, it is 3.86 kilonewton per meter. The question is why we call it tensile strength, why not we call it tensile stress? Reason being, the thickness component of these materials is very small in comparison to width and length. Therefore, we determine their strength per meter length, not per meter square. So that is the reason. So the variation in the first material, if you see, the variation in the tensile strength, it was 3.64 to 4.09. For the second material, it was 5.85 to 7.84. For the third material, it was 7.79 to 13.75. And for the third, it is varied from 30.3 to 33.64. That was the variation. Now, question is which values to be taken? Then we took the median of all the 5 samples which we tested in the machine as well as in the cross machine direction. Simultaneously, we have determined its variance. So you see, the variance is within the limit. Only 2 to 3% variation is there, but the median values are there. So median values, they are considered as the tensile strength of these products with a variance of 0.03 in the first case, 0.61 in the second case, 3.11 in the third case, and 1.81 in the third case. Similarly, you see the tensile elongation. Variation was 17.68 to 20%, 17.5 to 23.5% for the second material. For the third material, it was 20 to 26.67. For the fourth material, it was between 41 to 43. So the median value is taken as 42, here it is taken as 25.4, 20, 19.6. And the variance is again within 10%. If you see, within 10% variation is acceptable for these kind of materials because they are made from natural materials which has a lot very variation in the fiber diameter, in the yarn diameter, and finally we are using the same yarns for the manufacturing of these products. So that's why the variation in strength is going to be there. So that means this way you need to see that what are the things which are contributing to the strength. So this is all related to the woven geotextile. Now if we take the case of a non-woven geotextile, so this is all related to the non-woven geotextile. So roll length, roll with mass per unit area. So this is true in this case also. Larger the mass per unit area, larger is going to be the strength. But the strength, if you see, it is 15, 7, 2, 1, approximately 1.7 in the machine direction. So now we'll see that for what reason we are getting lesser strength for the first material. So here you see the aperture size of the PP netting, it is 20 by this. Diameter of the yarn top netting, it was 0.25 mm. Dia of the yarn top netting, 0.2. Mass per unit area of the bottom PP netting, it was 4.8 gram per meter square. Aperture size of the bottom PP netting, 9 by 9. Diameter of the yarn of the bottom netting, 0.18. So all these factors basically, they are answerable, they are responsible for contributing to a strength of 1.7 kilonewton per meter in the machine direction to the type J kind of non-woven geotextile. So the procedure followed is similar, but the strength you are getting very less. And this lesser strength is basically because in case of non-woven material, the loose web doesn't have the strength. The entire strength basically comes because of the scrim which we provide, because of the netting we provide, because of the stitching which we use in one particular direction. So all these parameters, they basically contribute to the tensile strength of these non-woven kind of materials. And same thing is the tensile elongation. So if you take a loose web and apply a tensile load, the strain is going to be almost zero because it is going to come out. But because of stitching provided on both the face or on a single face by the use of natural yarn or PP yarns, these materials show you some strain, and the strain, median value of the strain is varying 35% for the first material, 31 for the second, 12 for the third, and 26.75 for the last material. So last material we are getting a larger strain in comparison to this one. So you can also look for the reason of this one. So reason below, you will be able to get the reason from these parameters. You will see whether the aperture size is larger or smaller, what is the diameter of the yarn used in stitching, and all these factors, they are going to contribute to the strength, right? Is my voice clear?
Yes, sir.
Okay. Oh, बीच में break हो गया था link. So that means for these non-woven types of geosynthetic product, basically whatsoever we provide onto the surface to stitch them together, to bind them together, or to even in certain cases we use some adhesives also to join the loose web fiber together. So all these small things, they basically contribute their tensile strength in actually, because the fibers do not play any role in case of the non-woven geotextile. So this is the main conclusion which was drawn from the study reported by Rao et al. In 2009. So these are the two conclusions which I am just going to read right now. The woven coir geotextiles, they have more tensile strength in the machine direction than in the cross machine direction, and this reason for this is because more number of yarns along per meter length along the machine direction in comparison to the cross machine direction, because their aperture size may not be uniform in both the direction. On one side it may be having a smaller dimension, a smaller aperture value, on the other side it may be having a larger. So the number of yarns along the machine direction could be more in number per unit length, and it can be less number of yarns per meter length along the width of the roll. Right? So the tensile strength is influenced by the number of yarn. That is the main conclusion. The non-woven geotextile have more tensile strength and tensile elongation in the machine direction than in the cross machine direction. And the reason for this is because we are providing the stitching or the scrim is provided along the machine direction, not in the cross machine direction. We do the stitching in the machine direction only, and that is why we are getting more strength in the machine direction than in the cross machine direction. The other conclusion which is drawn, the behavior of non-woven coir geotextile is influenced by the presence of type of stitching, what type of stitching we are using, what type of yarn we are using in stitching, whether we are using a coir yarn or a jute yarn, or we are providing a coir netting or a jute netting on both the faces, and the coir web weight. Coir web weight contribution is very little, whereas the stitching, the yarn used for netting on both the faces, whether we are using coir or jute yarn or the PP yarn, all these materials basically they are contributing to the strength of the non-woven geotextile. Now the variance in the tensile strength and the tensile elongation of the non-woven coir geotextile is generally more in comparison to the woven coir geotextile. So this is true because the woven geotextiles, they are manufactured from the yarn which is prepared by the use of some machine. So their quality control is better. Whereas the non-woven geotextile, only loose web, they are put together and the stitching is done or the needle punching is done in one or the direction or the other direction. That is why the variation in strength is going to be more in case of non-woven than in comparison to the woven types of geotextiles. Now, if we look at the application of the natural geotextile in roadways in India, so long back in 1988, Kathgodam in UP, this was the first time the coir netting was used. Muzaffarnagar 1989, Bhangi Chobridge, Hoshiarpur, Punjab 1997, jute wovens were used. Chintal or Veru Bridge approach, Andhra Pradesh, again 1997. Trench drain, fin drains, they were all made from the naturally available fibers. UP in 1996, Hanuman Setu flyover in Delhi, Okla flyover again in 1996, as separation and reinforcement, Kakinada Port Trust 1995, Kandla Port Trust in 1997. So you can just see that we have started using these products 20 years back, but still because of the inhibition of their durability, people are not trying these products to a greater extent. Now we'll come to the one of the study which was conducted at IIT Delhi in the year 2002. So I'm going to tell you about that study. The application of these coir geotextile, it was explored in the unpaved roads. So you know, unpaved roads, they are a two-layer system. You have the subgrade, and above the subgrade you have either the main course, base courses, straightforward. And these are kacha roads or the village roads, which are sometimes provided for connecting the remote areas or even some access roads to the project site. They are connected by the use of these kacha roads. Now, if these kacha roads happen to be on a soft kind of soils, now in that situation it is going to be very, very problematic. And if you if you replace the subgrade soil with some good quality aggregates or good quality sand kind of material, then that is going to be very, very costly. Now, what can be the cheaper solution for this? Now we are going to discuss about that particular aspect. Now, if you see the most recent report of Pradhan Mantri Gram Sadak Yojana, not many villages with a population less than 1,000, they are yet to be connected. Around 2 lakh of villages, they are yet to be connected. And I am giving you this data from the southern part of our country. And majority of the rural roads or the village roads which are to be constructed, they are going to pass through the soft soil, right? So if this soft soil is actually going to be there, in that situation, it is going to be very much problematic, because during the rainy season, you will find many rutting actually is going to take place on the surface when the load is going to move over these roads. So the question is how to overcome this kind of difficulty. So for this purpose, a model study was conducted long back in the year 2002, where 2 types of woven coir geotextile, type A and type B, were taken. The details of the properties of these 2 materials, they are given in this table. So I am not going to read all these properties, I am just skipping this. And the third, this is the type A material which was used in this study. So you can see type A, this is type B, and you see type B has lesser aperture size in comparison to the previous type A. That means type B is going to give you more strength in comparison to the type A. Then we have used one non-woven type of material which we call as the type C. And if you look at the tensile strength of the type C material, it is only 1.7 kilonewton per meter. But if you see the tensile strength of type B is 31.5 and type A is 11.45. So you just keep this tensile strength in mind. So this is type C material, where it is all loose bed. Stitching is provided with the jute yarn along the direction of the road. This is a small sample just taken out from the main roll for the photograph purpose. Now you can see the unevenness also. Even at some location you are able to see on the other side, whereas at some location the web is thicker, whereas at other location the web is thinner. So you are able to see the things onto the other side, but at some location it is not possible, right? So because of this, you get the variation in the strength of these products. Now, this is the sand property which is used in this study. I am just giving you quick material properties. So you just remember these are the sand properties, and the next slide I am showing you, these are the kaolinite properties, which were kaolinite was used as a soft clay for this particular study. So here you see the properties of the kaolinite which were used, and this is the test tank which was used in this study. So these are the unit weight of the sand and the kaolinite clay which was tested, and in between the upper layer was sand, lower was kaolinite. In between we have the coir geotextile. The load was applied using a mild steel plate of 75 mm by 75 mm. Now if you see the curves, load versus or the bearing pressure versus deformation curve. So here you see without reinforcement your curve is like this. So that means it is attaining some value here, and then it is going parallel to that means there is no change in the bearing pressure. It's a constant, it's a punching kind of failure which is occurring below the load. But if you put a geotextile type A, type B, type C, you will find that though there is no increase in the bearing pressure up to certain level, but beyond certain deformation, you will see a large number of there's a sudden increase in the bearing pressure values. The bearing pressure is going up and up and up continuously. So this indicates that these kind of materials can be a very good material where the rut depth is going to be a major problem. Where rut depth is basically when the wheel bullock carts, they move over the kacha road, they cause a deep depression onto the road surface. So that phenomenon is called the rutting, and where the rut depth is going to be larger, and sometimes this rut depth can be as large as the thickness of the base course, and in that situation things will reach up to the subgrade. So therefore this kind of material is going to give you a better answer where rut depth requirement is high, and the bearing capacity improvement is our second target. So if you make the comparison, so you see type A is somewhere here, type C is somewhere here, type B is somewhere here. Type B has, please remember, type B has the highest strength. Type A is having the next to that, and type C has got the least strength. So if you compare type C with type A in this diagram, type C is giving you better strength, better improvement in the bearing pressure in comparison to type A. Now what can be the possible reason for this? Can you answer? Can anybody answer what can be the possible reason for this? If you look at the aperture size of type A, it has a more 11 point something is the strength value, and type B is having around 31.5 kilonewton per meter. Aperture size of type B is smaller than aperture size of type A. But if you make the comparison of type A with type C is having loose web, where the contact with the subgrade soil and the sand is more, whereas this contact is less in case of type A. That's why type C is giving you more, you can say, more bearing pressure at the same deformation. If I compare here at 50 mm deformation, it is giving you more bearing pressure value in comparison to type A. So because the contact area of this type C is larger in comparison to type A, because of the presence of the aperture in type A. So in some of the area there is no contact of the soil with the geotextile or the yarn of the woven type of geotextile. But in case of non-woven, the everywhere some are small fiber or maybe more number of fibers, they are in directly contact with the subgrade as well as with the base course soil. So that's why type C is behaving more better in comparison to type B. But in case of type A, because ultimately the strength is larger, aperture size is small, contact area is larger in comparison to type B, so it is giving you better answer, better improvement in the bearing pressure in comparison to type B. Now these are now in order to make the comparison of the coir geotextile with the polymeric type of geotextile, one of the earlier study reported by Shiv Gopal in the long back in 1993. He conducted the study using one non-woven geotextile made of the PP white little punched woven geotextile polypropylene की बनी है. Then the other one is a black PP grid, black biaxial grid was used. So in both the studies, polymeric material was used. Now if you look at the bearing pressure versus deformation curve, so these are the sand properties, Delhi silt properties which were used in that particular study. Now if you see the diagram, these are the curves corresponding to the Shiv Gopal's study which was reported, whereas the study which was conducted in the 2002, all our bearing pressure versus deformation plots, they fall in this particular region. Now the question is, there cannot be a direct comparison with this kind of situation. Reason being, the subgrade soil used in case of the study reported by Shiv Gopal, it was Delhi silt, whereas the soil used in the study reported in 2002 was a kaolinite clay, which is a soft clay and having very less strength in comparison to the Delhi silt. Number one. Number two, the geotextile and the polymeric geogrid was used in the study conducted by Shiv Gopal. Whereas in this case, the polymeric material was not used. It was the coir geotextile which were used in this particular study. Therefore, in order to have the comparison among these two studies, we need to normalize both the studies to bring them to a single scale. Now that normalization basically we have conducted by determining one factor which we call as the bearing capacity ratio. So if you see the BCR is basically the ratio of a reinforced bearing pressure to the unreinforced one. In both the studies, we have calculated all those values. And now you can see that if you see the BCR, these are the 2002 study which is reported, type A, type B, type C, whereas the Shiv Gopal study is giving you somewhere here. So that means these products, they are equally, you can say, equally good in comparison to the polymeric material used by Shiv Gopal in 1993. Reason being, because they are giving you same level of improvement in the bearing capacity, in terms of percentage improvement, right? Because BCR is a dimensionless parameter. So if you make the comparison, the level of improvement is going to be similar in both the situations. So this is the main conclusion which were drawn from this particular study. So if you permit me, I will continue. Otherwise, I may stop at this level. Please advise. So this is one analytical model which was given by Bird in 1995, and these are the parameters which were used. So type A and type C type of material was basically used to check the validation of this model. So this is the Bird's 1995 model, gives you, this is my actual curve, experimental curve which I obtained. This is the curve which I obtained from the Bird's model. So here what you see, in the initial part of the study, you see the stiffness predicted by Bird's 1995 model is much higher, whereas there's an improvement in the prediction once at larger deformation. If you see at this deformation, both the curves are approaching towards each other. That means the Bird's model, it overestimates the stiffness of the model which we have taken for the study in the beginning. This is the limitation of the Bird's model. This is with type A. Similar conclusion was drawn using a type C material. Then finally, this was the main conclusion which was drawn, and the similar kind of conclusion was also reported by Mahmood et al. In the year 2002. In the year 2000 also, that the Bird's model, it gives you overestimation of the bearing pressure in the initial part of the curve because of the non-inclusion effects of the elastic soil deformation at small deformation. So this was, our studies conclusion conducted in 2002 also matches with the conclusion drawn by Mahmood et al. In the year 2000 also. Now this is a repetitive load test. Repetitive load tests, they were conducted and compared with the earlier study reported by Shiv Gopal, where the polymeric geosynthetics were used. So now here you see that when we increase type A, type C at different repetitive loading we have done. So as we increase the load, so you see the deformation, the permanent deformation is going to be lesser with the insertion of with the introduction of the geotextile, quartz geotextile at the interface of these two layers. So this is the main conclusion which we have drawn out of the repetitive load test, which is reported in the year 2002. So again, this is a comparison of percentage reduction in the permanent deformation in the study conducted in 2002 and the one which is conducted in 2009. So in both the studies, this is 2002 study, this is 1993 study. So here as you see, the percentage reduction is more or less matching with the earlier study. So that means from this we can concretely say that coir products, they can be used in conjunction when we need to construct the unpaved roads or the rural roads, especially over the soft soils which are there, because they are pressure, similar amount of reduction in the permanent deformation under the cyclic loading. So this is the main conclusion which were drawn out of this particular study. So finally, there's another advantage of using coir geotextile in unpaved loads. That is that these materials after 2 to 3 years, they are going to degrade. And once they get degraded after a period of 2 to 3 years, they are going to act as a filter, or for drainage application and for separation application, they are going to be there permanently. So that means these materials, even after degradation, they are going to perform some other roles which are required to be performed by these materials when used at the interface of the soft clay as well as some granular material. So with this, I just close my lecture. Now say thank you to everyone for the patient listening and coping up with my speed. And now if you have any query, please raise your doubt.
Sir, the queries would be in the chat box, I think. All the participants.
You read the chat box and just tell me so that I can.
I request all the participants to please put the queries in the chat box. Or sir, can they interact with you? Can they interact with you through verbally?
Yeah, directly they can interact. That is better.
So yeah, one by one the participants can interact also.
देखिए जिसने बात करनी है वही अपना माइक ऑन करेगा, नहीं तो वो इको होगी. ठीक है, चलिए गो अहेड. कोई नहीं दिख रहा है मेरे को अभी.
Sir, I think there is one query in the chat box. Let us take that in the meantime.
बोलिए.
Which one is the more durable? N2M3, H2M5, H2M8?
Say durability, I told you, whether you use H2M3, H2M5, H2M6, anyone, the duration is going to be between 2 to 3 years. But if there are studies reported in literature, if you use these material in conjunction with water, their durability is up to 5 years. That means if we want, you might have studied some of the papers related to scouring around the bridge piers. People are trying these material. The people are using different types of structures for reducing the scouring around the bridge piers. Why to use those structures? You use coir because it is going to be there inside the water, and it is going to be there for a longer period. So that is a cheaper solution, and the replacement is easy. You need a mat, and the mat is to be tied to the around the bridge pier so that the scouring may not occur. That is a better solution. Any more queries?
Participants, any other query, please ask sir. verbally.
Anyone who wants to work on this area for their PhD, I can give you many clues. Now the main question is how to improve the durability of these materials. There are different types of polymeric material available in the market. You can those materials are soluble in water. You can use them, treat these coir fibers or coir geotextiles to improve their durability. They provide a coating around these coir geotextiles. This is one solution. There can be many alternative solutions. You can study the degradation behavior of these materials. Just put them into different environment under different temperature and humidity condition. And after that, take them out, go for the SCM, see why the degradation is occurring at a specific location. What are the causes of that degradation? And look for some nanoparticles to graft those nanoparticles into the coir geotextiles so that as and when you test them again in the same incubator at same temperature and humidity, probably you will get better durability because you have replaced those spaces with by grafting those nanoparticles which are not going to degrade under the microorganism attack. So any more question? No question?
I think, sir, there are no queries.
Okay.
Yes,
Okay,
sir.
sir. Okay, sir. Thank you.
Thank you, sir. We should be thankful to you. You accepted our proposal and gave a very nice presentation. And it was nice seeing you again, interacting with you also.
परंतु मेरे को एक नाराजगी है आपसे.
सर क्या नाराजगी है?
आपको मेरे को ना पॉलीमेरिक जियोसिंथेटिक्स पे देना चाहिए था टॉपिक. I could have told them many information. Required was though because the majority of the things I presented from my PhD thesis.
Okay.
But I could have given them better on polymeric.
Sir,
So that,
we would like to have webinars on this thing. Like if you want
you can because I want to show them the variety of application of the polymeric geosynthetic which we are doing at present in the country.
Okay, sir. Then
you can fix some other day. You can fix some other day there and give me at least 2 hours time with the 5 minute break in between.
Yes, sir.
Okay,
Definitely.
sir. Okay. Thank you,
sir.
all.
Yes, sir. Thank you very much.
Okay.
So participants, that was Dr. R.K. Datta sir from NIT Hamirpur. He gave a very wonderful presentation on the use of geotextiles. So now I would like you all to just look over emails in a couple of hours and check out for the feedback link and fill that form for getting your participation certificates. Okay, so those who will fill the form will only get the participation certificate. So I request you all to fill the form properly and put your name as you want it printed on the certificate. So please look for that. Now, in the end, I would say that it was a very nice and wonderful experience interacting with you people and having you around us on such a endeavor towards influencing the people and circulating knowledge among us them. I'm thankful to you for your motivation as well as your presence here at this STC. Thank you. The Civil Engineering Department congratulate you and also is thankful for your whatsoever help which you have provided us in participating in this course. Thank you for being with us. Thank you,
sir.
Okay.